going straight to the problem. A, identify the carbon atom that's migrating and draw a mechanism for this carbocation rearrangement. Okay, over here, the main carbon that's moving around is this one. This carbon is responsible for this rearrangement because it's gonna push this bonding electron toward that carbocation. And in the process, we're gonna get the 3 ring, that's our pentagon. Over here we have a hexagon and a square attached to the pentagon on the bottom. The bottom pentagon is intact, but then the top part is now changed to 2 pentagon instead of 1 hexagon and square. So this is one easy way to show the mechanism. And to answer our part B, it's a little bit more complicated because okay, let's read it first. The process is to be diastereoselective because only one of the 2 possible diastereomeric carbocation is formed. In other words, it's saying we only got the dashed line here. Why can't we also have a wedge methyl group sticking toward us? Experimentally, we're not seeing that. We only see the dashed. Well, part of the reason is this is going to be very specific because we have a 3 ring, and when you have this many rings, the single bond, despite single bond can rotate easily, they are not so easily rotatable. So it's pretty rigid. In other words, these bonds you see are all very stuck to each other. So it's going to be very specific whether the methyl group is sticking toward us or pointing downward. And the reason for that, that's one reason. Another reason is if we draw this in perspective, or from the drawing of the molecular kit, I can also show you that the p orbital, the empty p orbital, is going to be on one face of this ring system. So I can draw the left side structure as like this. Okay, this is the hexagon that I'm drawing. You see 1, 2, 3, 4, 5, 6 carbons, and let's say that's popping toward us. So I draw the quite thick wedge lines over here, and then our methyl group just go that way, still on the page of the plane of our page. And where is it? And we have a methyl group that also gonna, stick toward us. Now, even though it shows a dashed line, it's gonna be really thick line here because we're kind of seeing from this perspective. Here's our eye. We're seeing this, but still from the top view. That's why we see these dark lines here. And then we have a square next to it, and I can draw it like just this to give the perspective. And then finally, this one, when we see from the top, the bottom pentagon, that's gonna stay away from us. But from this perspective, from this angle, we're gonna see it more coming toward us. So we have the pentagon here. So I'm gonna draw all thick lines around it, just to show you that it's popping toward us, and that way it adds less strain between the rings. Okay, so this is what we see, and then we have a carbocation on this specific place. And then as you see this, okay, oh, I think I forgot okay, there gotta be another. Okay, this is a kind of away from us. The methyl group is kind of pointing that way, and I also forgot another methyl group here. Okay, but what's important is that line you see, I'm gonna draw a red line over there, really correspond to this for now. And when it shifts to that carbocation, you're gonna form that carbocation to the next place. So this is going to be it's more like this now. That red is now over here. Now if you see it, what was on the plane of this page now becomes going away from us, and I can finish this having the rest of the structure drawn. Okay, there's no change in the drawing for our front pentagon, and this method sticks up, and then I'll draw this another method kind of pointing toward below the page here, or below this plane. Okay, so now I have a new carbocation on this place. Okay, there's no hydrogen attached. And you see from this picture, if these three lines, the single bonds, are on the plane of this page, then this is gonna have the sp2 hybridization, and the empty orbital is gonna be either bottom or top that interact with our bond, the red color here. So from this drawing, it looks like it's gonna interact on the top of this ring. And when you interact by forming a new bond, you can kind of visualize that this ring is now pushed kind of toward us, and in that process, this methyl group get tilted back. Okay, and another way we can also justify that this is tilting back is not only that, but also we're gonna have this methyl group, kind of like 1,3 diaxial, although it's not really diaxial, not necessarily diaxial position, but you can see some kind of steric hindrance between this methyl and that methyl. If this is the wedge, okay, again, not the dash. If it's wedge, you're gonna get that kind of, you can possibly get the steric hindrance. So that's why we have this specific dashed line instead of wedge, and we don't see the wedge structure for part B. Okay, and to answer our part C, in this case, a tertiary carbocation is rearranging to give a different tertiary carbocation. So just a driving force for this process. Well, the main reason is you have a huge angle strain that arises from that square here. Remember that the square, the cyclobutane, really has this structure. It's not really getting 90 degrees. To alleviate some torsional strain, it's like 88 degrees, but this is very not stable form compared to the cyclopentane or cyclohexane, as you see here. So but then you also have to say we have a very stable hexagon here, cyclohexane. So it's like by creating cyclohexane to cyclopentane on the left ring, you can see that our stability went down, right? So more energy is involved here. But we had the cyclobutane that became the cyclopentane, obviously the stability goes up and less energy involved. The universe pretty much favors the lower in energy. And we have two interacting forces here. And to answer this driving force, why this happens, why it favors this three-ring structure in which all cyclopentanes are favored. The reason has to be the magnitude of the stability. Okay, so from cyclobutane to the cyclopentane, gotta be much bigger than the magnitude that strains the stability and that creates more energy in the system. So as we release more energy and create higher stability from turning the cyclobutane to cyclopentane, this net stability is much more from transitioning from cyclobutane to cyclopentane. That's the driving force for this to happen.